Hello everyone. We talked about two different variables before, numerical variables, categorical variables. There are four different data measurements scales as follow: nominal, ordinal, interval, and ratio data. These are all subcategories of categorical and numerical data. Nominal data is defined as data that is used for naming and labeling. Naming and labeling. There is usually no ordering to nominal data. Nominal and ordinal data are all under categorical variables. And interval and ratio data are all under numerical. So nominal and ordinal under categorical variables, then ratio and interval data are under numerical variables. Okay, so nominal data is a group of non-parametric variables, while ordinal data is a group of non-parametric ordered variables. For example, rate your satisfaction with a product, scaling from 0 to 10. This will be all ordered from 0 to 10, right? So we call this type of variable ordinal numbers, which is again, this is a subcategory of categorical variable. And then we can say rating the weather like hot, cold, moderate. So this type of variable can be nominal variables, and this is also subcategory of categorical variables. I found this nominal and ordinal variable more difficult to distinguish or recognize in compared to interval and ratio data, which are much easier. I mean, generally numerical variables are much easier to realize than categorical variable. Okay, so today we want to talk about linear regression. So to understand linear regression, we must know the type of variables, we must know what kind of variables we are dealing with. And because this analysis, regression analysis, is a commonly used predictive analysis. We can predict a variable based on another variable. As a review, last time we talked about response variable, explanatory variables. Explanatory variable can affect response and cause a change in response. So explanatory variable cause changes in response. And there's another thing about explanatory variable, we call that predictor. Why? Because we can predict the response variable using explanatory variables. Okay, so let me write this down. I will later copy paste all my writing here. We can predict response variable using explanatory variable or variables, right? Okay, so explanatory can affect response and cause a change in response. We can also predict the value of response based on the changes that explanatory variable causes. So for this reason, we call explanatory variables predictors, and the response is being predicted by explanatory variable. So we can use actually regression when we are dealing with response variable and explanatory variable. Imagine response variable is dependent variable and the explanatory variable is independent. So we can observe the changes that causes the changes in the dependent variable that caused by independent variable. So I'm going to write down different name of these two variables: independent variables, response variables, y also, and predicted. Oh, so here my mistake. Dependent, right? Okay, and then x is, I'm going to copy this here, independent variable, and explanatory, and what else? Predictor. Okay, so the idea is to examine if a set of predictor variables x do a good job in predicting the response variable, or which variables in particular are significant predictors of the response variable, and in what way do they impact the response variable. These are all the questions in our mind when we are using regression analysis, and regression analysis can explain all of these questions. Okay, so the simplest form of regression is when we are dealing with one dependent variable and one independent variable. One dependent variable and one independent variable. Okay, so when we can use a linear line in mathematics, the linear line is y equal a slope multiply x plus a, which is the intercept, right? So what is b? B is slope of the line and a is the intercept of the line. So a slope could be positive, a slope could be negative, right? And then a slope says based on 1 unit of x, y will change b unit. So this is the definition of a slope actually. So we call the simple form of regression a linear regression. In parentheses, this is linear regression. And as I explained, you are dealing with one dependent variable, which is interval or ratio. So when I say interval and ratio, I mean numerical, right? Numerical variables. And then you are dealing with one independent variable, which could be interval, could be ratio, could be also category, but a kind of binary category, means just two groups, only two groups. Okay, so there are different types of linear regression as well. We have different types of linear regression also. For example, we will talk about multiple linear regression, and then multiple linear regression says we are dealing with one independent variable, which could be again interval or ratio, and we can deal with two independent variables, two or more, right? When I say 2 plus means 2 and above, variable or variables. And then they can be interval, ratio, binary, all of them. And then we have, let me put a star here so you know these are the type of regression. Then we can have logistic regression when we are dealing with one dependent variable and one or more independent variables. And then we can have multi nominal regression when we are dealing with one dependent variable, which is nominal, and one or more independent variables, can be interval, ratio, or binary. And another one, discriminant analysis, which is a form of regression analysis whenever we are dealing with one dependent variable and one or more independent variables. So as you see, all these different regression type that I'm talking about, we are just dealing with one dependent variable, one y variable, and we could have one or more independent variables depend on the type of them and depend on the name of these variables. I mean the number of variables. We can have different analysis, which are all of these I mentioned are under regression analysis. Okay, in this course we will definitely go to simple regression, and maybe we go to multiple linear regression, and we will talk about polynomial also models. So as much as we can, and you need to know, we will go through the regression, because regression is a very useful regression analysis is a very useful tool. Okay, so generally we use regression to analyze the changes in response that's caused by the other variables, explanatory, or we call that predictors. Then we can also predict the future outcome. When I talk about prediction, so we can talk about the future outcome of response based on the changes of the predictors. So now when we use regression analysis, we try to model the relationship between variables, or even we can control one explanatory variable to see the effect of other variables on the response variable. Then we try to fit the model. That's important also. So therefore, to interpret regression output, first we need to fit the model and verify that we have a good model, which is a really kind of sometimes depends on your data set, it will be a very difficult task. Okay, so now there's a concept named coefficient of determination. We'll go in detail when we have the output of our analysis based on the data set we have. We talked about coefficient of determinations, which is a very helpful tool in explaining the variability of response variable explained by the model we are going to create or design, because this explained variance of the model can easily increase if we add explanatory variables to the model, or it can easily decrease, means coefficient of determination can easily decrease if we remove some explanatory variables and if we don't have enough predictor. So what happens if we add more variables to the model? We can accidentally increase the variability. We can cause overfitting. So overfitting is a very kind of famous concept or error in regression analysis. So whenever we add so many explanatory variables and our model have extra explanatory variables, we call that which cause a higher variance variability in the model, we call that overfitting. So overfitting can cause lots of misleading information. Therefore, we always prefer a simple model that can be more beneficial than a very complex model which is overfitted. Also, there is another concept which is very important, underfitting. Okay, so underfitting also occurs when a model cannot accurately capture the dependencies among the data, and usually when the model is too simple, that causes underfitting, and if often yields this kind of overfitting and underfitting can often cause a high R-square or coefficient of determination, or low or high coefficient of determination. So this is important also. R squared. These are all the important concepts in regression analysis. We should pay attention to all of these. Okay, so now I want to show you some graph. So you already know what is the scatter plot, right? So I also explained that on y-axis we have response variable, on x-axis we have explanatory variables, and each of these dots shows an individual in the study. For example, if we have students in the study, x can be the amount of time they spend the study for the exam, and y can be their exam score. So x can affect on their exam score, means the amount of time they spend studying for the exam can have effect on their exam score, right? So each point here shows a student's grade and a student's study time. Okay, so the red line shows least square regression line, which is showing the predicted response for each of these points. So what is the predicted response? For example, this student who is studying this much get this exam score on y-axis, which is the observed exam score, for example, can have a predicted exam score which is kind of captured by this least square regression line. So each individual can have a study time, explanatory variable, right? It can the individual can have exam score, which is the observed y, and also an individual can have predicted exam score, which is a predicted y, predicted response. So when a point is under the line, the difference between the predicted y and the observed y is negative. If the point is above the line, the distance between the predicted y and the observed y is positive. So for each of this point, we can have observed y, we can have response y. The distance between the observed y and the predicted y is error. So for each point, we can have error, right? Which is observed y minus the predicted y. This hat above the yi shows the predicted y. Response minus predicted. Error for the point above the line is positive, for the point below the line is negative. So we call this error or residual. Okay, so the model that I was talking about, for a simple linear line, we have intercept, which we show in statistics, we show that in regression analysis, we show that we B0. And then we have a coefficient for explanatory variable, which we show that with B1, for example, if we have just one explanatory variable, and just assume, just imagine if we have more than one explanatory variable, the next explanatory variable will have B2, B3, B4. For each of them we will have a coefficient for each of the explanatory variable. For example, this explanatory variable says a study time, right? The other explanatory variable can say like age of a student, right? We want to see what's the effect of both age of a student and a study time on their exam score, which is response. So what is error term? Error term is all the error that we have in the study. Okay, so method of least squares says the square of residual or error is equal to summation of y minus what is that? Predicted y power 2, right? And then if you look at that here, we can see it actually here, this one, this formula. We call that SSE, the sum of residual or error, sum of a square, error. So will be this formula, right? This formula is exactly same as what we have here. We have yi, which is each response variable, and then y hat is the predicted response for the individual I. Okay, so SSE is very important, and as you see, if this is a point, if this is a observed point, observed response, which goes on the axis y, and it will be here, the distance between the least square regression line to the point is SSE, sum of a square for error, and then SSR is SS total minus SSE, which is the summation of each predicted y minus the whole mean of observed y. If we go to this formula, we will see SS total, sum of a square total, is summation of each observed y minus the whole mean of y value power 2. So these three formulas are very important, and you see that we show them in here. We show each of these distance in terms of sum of a square error. Okay, so the coefficient of determination, which is r square, tells you which amount of variation in y, observed y, can be explained while depending on x value based on the regression model we create. So how good this regression model can explain the variation of y based on the depending variable x. So the larger r square indicates a better fit, and that means the model can better explain the variation of output with different input, right? But sometimes this r square can be misleading, so we always must be very careful, because r square can change based on some error like overfitting or underfitting that I explained here. And then the value of r square equal 1 correspond to sum of a square residual here. This one equals 0. So r square equal 1 means SSR equals 0. So that is to the kind of perfect fit if we have SSR equals 0 or r square equal 1, right? It's a kind of perfect fit because the residual error will, the sum of square error will be 0, right? Okay, so that's a perfect fit if we have a r square equal 1 and the values of predicted and actual responses fit completely to each other. So as one of my participation point question was about that, I said if we have a point on least square regression line, what is the residual for that? Residual will be 0. What is the predicted y for that? Predicted y will be exact same as response y or observed y. Okay, so now let's close this and let's start some coding here. Let me create some of the cells. Okay, so now some of the packages that we are going to use, as you know, is NumPy, import pandas as PD, and then let's graph, also use graph package .pyplot as PLT. And then now we want to, so for regression analysis, I'm going to use different packages and show you different ability these packages have. One of these packages I'm going to show you this time is import sklearn dot linear underline model, and I'm going to say as SKLM. Okay, so I have actually a new data set. Let's bring the data set here. It's a data set for serials, and I'm going to read the CV and CSV, sorry. And then I'm going to print the data set. Oh, what I'm doing here. Let's print the data set. Let's print 10 of them, okay. And I'm going to print, I want to print the shape of data set, means the dimension of data set, or rows and columns, number of rows and columns of data set. How can I show that? Do you remember we use data set dot shape, right, without parentheses. And then I'm going to print, let's print what's that, print each of them in a new line. And then I'm going to print the statistic of the data set. If you remember, we could use describe to print the data set. statistic of data set. Okay, so this is the data set. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 columns, which shows here, and 77 cereal. These are the name of cereal. For each cereal we have type of them, calories, protein, fat, sodium, fiber, and weight, every aspect of this cereal. And then we here show the statistic for each of these columns or variables. Calorie is a numerical, protein is a numerical, fat, sodium, fiber, carb, all of these are numerical. The cup, actually, let me see, number of cups, actually that's a measure, yeah, that's a numerical variable, right? And the rating, people's rating also. So we have mean, standard deviation, the first quartile, median, and the 75 percentile, or the third quartiles, and maximum. So we have all this information, right? Now what I want to do, I want to import skyp.stats as, to make it funny, spicy. Okay, print spicy dot, do you remember Pearson R? We want to find a correlation between some of these variables. Data set dot, which one? Sugar. Let's see, where's sugar? Here, this one, this column. Sugar. And what else? Data set dot calories. I want to see what is the correlation between these two, and then I will use 0 because Pearson has two output, two index output. I'm going to extract the first index of this output, and then I'm going to, okay, let's see what's the Pearson correlation. Data set is not defined. Why? Because it's wrong. Okay, so this is a correlation. Okay, so for your participation point, calculate the other correlation I explained and last time. So give me the value, exact value, means with all the decimal you get, and I want also you to find a correlation for, let's say, weight and carb, correlation between weight and carb, and then correlation between protein and calorie, correlation between fat and also calories. So find a correlation between these using the other correlation I talked about, and explain to me what is the benefit of the other correlation we talked about, and you are going to calculate what is the benefit of that using that other correlation. So now we know what is the correlation between sugar and calorie. Let's create some plot. Okay, so I want to see the scatter plot of sugar versus calories. And what I want to do, using a slope and intercept, I want to find some of the characteristic of this least square regression line using slope B and intercept A. I like to find the least square regression line for this purpose. I'm using polyfit from NP package. Okay, so what I do, the first argument will be the x, the second argument will be y, and then 1. First argument x and second argument is y. For example, here I want to see what's the effect of sugar on the response variable calorie, how sugar affects on calorie. So let's say x is sugar and y is calorie. Let's assume that we are interested in finding the changes caused by sugar, the changes of calorie caused by sugar. Sugar is x, calories y. So in all the studies, you must know what is your response variable, what is your explanatory variable, and you should have an idea what you are doing exactly. Okay, so I want to create a variable, we call that y hat equal to b multiply this is x plus a slope. What is this? This is the linear line with this one being the x variable, and then you already know what is b, what is I, and this will be the predicted y. This one is y hat is the predicted response. So what is the predicted response? Predicted calorie. Yes, okay. So I created y hat. I'm going to use this y hat to plot the regression line. Let me see what we have so far, because I have a scatter plot, right? To draw a scatter plot of sugar versus calorie. What did I do wrong? It says B and A NP polyfit is wrong. NP dot polyfit. Okay, well, this line has something wrong, maybe a spell or something I did wrong. So what happened was my NumPy package was not installed because I kind of updated pip, so for that reason some of the packages were not defined. So you may encounter this kind of problems. Just remember, Google it and you will find a good solution. and then don't update the packages without any certain reason, because this kind of problem will happen. Okay, so let's go back to our model, our scatter plot. So what we did, we used a slope and intercept. So each of these will be defined using polyfit in NumPy, and it will create a kind of a least square regression line. So I have used a formula. As you see, this is a simple linear regression, and then I created all the y-hat, and now I'm going to plot this y-hat, all of these y-hat, which will create a least square regression line for us. So the second argument is y-hat, the first argument is the x value, and let's color this red, and then you will see there's a least square regression line created on this scatter plot. So on x-axis we have sugar, on a y-axis we have the calories. Okay, so let's create another scatter plot, and let's this time create a scatter plot of protein and calorie. So what we do, we actually do the same thing, but I'm going to change the sugar to protein. So here, everywhere I have sugar, I will write down protein. So this will be the scatter plot and the line of least square regression line. Let me see. Everything is okay. Oh no, here. Okay, so now look at this. So the relation between sugar and calorie is kind of showing a linear relation, and the slope is positive, means as sugar increases the calorie also increases, or sugar decreases, calorie will decrease. Here we have more a kind of zero correlation, and we can actually try this correlation by using the Pearson correlation. So let's see. So I want to see what's the correlation between protein, and look, the correlation is very small. So it shows that there is no kind of relation between protein and calorie. But in compared to this one, which has kind of, not a strong correlation. I mean, whatever is less than 0.7 consider as a kind of weak correlation, but it just depends on the study you have. Less than positive 0.7 and also negative 0.7. I consider those as a weak. So this is also weak, but not as weak as this relation 0.019, which is almost zero. So when correlation is closer to zero, we have a weak relationship. So now let's create a scatter plot of sugar and what is that? This time I want to create a scatter plot of sugar and protein. So this is protein, and I want to find a correlation between protein and sugar. And let's say everywhere I see calorie, I replace by sugar. Oops, sorry. Just for calorie, I replaced sugar. So look at this. So the sugar and protein shows a negative relation, which is still very small correlation. And then the plot is showing the negative slope, which is, obviously a negative correlation. So slope and correlation always have the same sign. So this is the way we draw a scatter plot and least square regression line. So in next video, I'm going to start using some technique to get some of the information of, first of all, create a least square regression line, and then get some of the information like a slope, like intercept, all of those. These steps were just the kind of basic to know what variables are related and what variables are not related, using the correlation, using a scatter plot and least square regression line.